So I'd like to introduce today's speaker, Marcus Rigol. Marcus is at Georgetown University now. He did his PhD in Stuttgart, Germany, spent a couple of years as a postdoc, and finally is here. So from my point of view as a cold atomic physicist, Marcus made his name doing quasi-thermalization in one-dimensional systems. And it looks to me that we're going to hear something related to that. So thanks very much, Marcus.
Thanks, Ian. So it's a great pleasure to be here. So as Ian was saying, I will be talking about the non-equilibrium dynamics of isolated systems and then relate that to questions of thermalization. So this is the outline of my talk. So half of the talk will go into the introduction, really, setting up the questions and reviewing some previous work, experiments that have been done recently. What is it that we mean by thermalization in systems that are isolated and which have a unitary evolution? And then I will show you results. I will serve an example for the rest of the talk about two extreme cases. Okay? So at this point, I'm essentially going to stop for a while and then going to take some questions before getting into the more technical part about what's really happening with the dynamics and how is it that we can understand it. Okay? And then the summary is going to come at the end. So you may imagine this is a topic that has been in physicists' minds for quite a while. As a matter of fact, von Neumann already thought about that in 29. So how to reconcile what happens in quantum mechanics and statistical mechanics. So he published this paper in 29 in which he claimed that he proved essentially ergodic theorems for quantum mechanics. Okay, so and that's a very very interesting work, rather technical. And, but that was not the end. So several years later, that work was criticized. And essentially, 57 was the year that von Neumann died, so he couldn't reply to this criticism. So, and essentially, well, there were several works there in the late 50s and 60s, and the whole thing seems to be kind of forgotten. So, more recently, people have started retaking these questions and started talking about typicality and eigenstate thermalization, which I'm going to mention here. And it turns out that all these recent things and concepts are certainly related to von Neumann's work. Okay, so essentially, I'm going to be telling you a bit about this eigenstate thermalization, and we're going to see how that is relevant to non-equilibrium dynamics of quantum. Now, in the days that von Neumann was thinking about that, there were neither computers nor experiments to really check these ideas. So computers became available after the Second World War, and as you may know, one of the interesting facts in the use of computers is that one of the first experiments, or numerical experiments done, was essentially thought by Fermi, Past, and Ulam to test the ergodic hypothesis for harmonic oscillators. So essentially, what happens is you put energy in some modes and have some nonlinear coupling. And the idea is that, well, one should see thermalization and ergodicity. So, but that was not what the experiment actually shows. So this machine is the Maniac 1 at Los Alamos, or where the actual numerical experiment was done. So essentially, they saw something that was surprising. So they saw quasi-periodic behavior and lack of ergodicity. So and that generated a lot of work. And people started thinking about whether that was related to Poincare recurrence. It was not. And then came the relations to the KdV equation and solitons and the importance of dynamical chaos for having ergodicity in systems. And this theorem, the KM theorem, about how far you have to go to away from some integrable point to see ergodicity and so on. And all these are essentially, basics in our modern understanding of statistical mechanics. So now all this was classical systems. Now more recently, experiments have come into play, and even in the quantum regime. And this has to do with these cold gases experiments, which many of the experimentalists here are doing. So since this is the most relevant case, I'm going to be talking about quasi-one-dimensional systems, because that's the kind of system I'm going to be discussing later in the theory. But essentially nowadays we have these cold gases which can load them into two-dimensional optical lattice and create quasi-one-dimensional system, and they are embedded in very high vacuum. So essentially one can think of them as totally isolated systems in which one can study the non-equilibrium dynamics, and one also has full control on the parameters of those that control the dynamic in the experiment. So for example, in this one dimension, one can fully control the interactions between particles. So at very low energies, they have this form, and this in one dimension can be controlled two ways. One is with the scattering length, the three-dimensional scattering length of the particles, and the other one is essentially the strength of the transfer confinement. So, for example, one can take bosons, and one interesting thing that you can do with bosons is you can make this term very close to 1 and lower the density, and these bosons in real space, they are going to start behaving as if they would be fermions. So essentially they are going to become like impenetrable. And this is a very interesting model. It was introduced by Girardot in the 60s, and it can be solved exactly. It's an integrable model. It can be solved by mapping it to non-interacting fermions. And this is very close to the models I'm going to be showing you later. So essentially, this was realized experimentally in the group of David Weiss at Penn State in 2004, and these results here are results from this experiment. What is shown here is this G2, which tells you what is the probability of having an overlap between two particles in the system as a function of this gamma effective, which is in here, is proportional to the G1D and inverse proportional to the density. And what is showing here, the points are the experimental data. So this Tons-Girardot regime is when gamma is infinity, but the line is essentially a theoretical result based on the linear model without free parameters. And what you see is that now in this experiment, what are really almost perfect control on what's happening. So the theory and the experiment match almost perfectly. So the other thing that one can do is introduce a weaker lattice along the one-dimensional tubes. And if this G1D is very large, essentially what's going to happen is that you will have a realization of another very interesting model of statistical mechanics. It's the XY model, which introduced by Lipschutz and Maddox in '61, and can be also exactly solved by mapping it to non-interacting fermions. So, and this was realized in this experiment here, and what is shown here is the momentum distribution function of the particles. The points are the experiment, and the line is the theory using this mapping that I was telling you. And here something to remember is that this instead is just the distribution of the density in the trap, and this is just to keep in mind that these systems are isolated and they are actually homogeneous. So essentially what we can see here is that now there is an experimental tool to really realize models, and now you can start playing with them. Now, while the theory in equilibrium is pretty well known, what happens out of equilibrium is something that is more interesting and about which we don't know that much. So I'm going to show you essentially simulation of an experiment also done in the group of David Weiss. In what he essentially did is he had these one-dimensional tubes in here, and if you are at low temperatures, the density will look something like that. There are few particles that there are the ripples here, and the momentum distribution function is going to be peaked. So what he did is he applied two laser pulses and depleted this peak into, he essentially split it, half of the particle almost were moving in one direction with some velocity and half in the other direction. And from there on, he just studied the dynamics. So, okay, so you see, you have a trap, you have particles overlapping, and then half of them moving in one direction, half moving in the other direction, right? So if this would be a normal gas, the ones that we are used to, so essentially while particles that want to escape from the trap start colliding, what will happen is you will have redistribution of momentum, and then the system will decay to some equilibrium distribution. So that should be a higher temperature. So, but essentially what they saw was something like that. So in the numerical simulation, I have some extra peak here because I was kind of lazy about depleting that. But the important thing is what's happening with the particles moving at some final momentum on the left and on the right. So what you see is essentially in this quasi-one-dimensional system, these particles, they collide, but still they can go out. There is the trap. That's why they don't escape. And then they go back and forth. And there was no sign of thermalization for several periods. Okay, so they went out, and so this is the theoretical calculation. So let me just show you the actual experimental data. So this is how it looks like. I mean, for a few periods, like 5, it looks that nice, but then it disappears. This is how it looks in theory. Ultimately, after over 15 periods, they did see that the distribution of momentum of the particle stopped change. Okay, so it was kind of steady. And what is shown here is that distribution for 3 different values of that gamma parameter that I was telling you there. Okay, so this gamma very large is close to this Girardot regime in which they are like infinitely repulsive. Okay, so now there is one thing that you can immediately see from here, right? So these are particles in a harmonic trap. Now you can immediately see that this cannot be the thermal distribution because the thermal distribution will not have these extra peaks. So this is something that is coming from that initial state. And this feature is very strong for large values of gamma, and it is less visible for higher values, for smaller values of gamma. And this is the lowest value of gamma that they can do, keeping the system still in one dimension. And that the distribution looks like that. It may look like thermal, but if you actually plot the thermal one, it's still different. Okay? So now there are many questions that you can ask about this experiment. So you can ask whether they waited long enough, and this is something that we are going to be discussing in a few minutes. How close is this dynamic to the real unitary dynamic of a purely like isolated system? And what is the role of, for example, when you move away from this gamma infinity, of this integrability breaking terms that you are going to have because you have the trap and so on. So, and many of these things we are going to be discussing here. So, one thing that I can show you is a more recent experiment that has addressed this question of how close is that dynamics to the actual unitary dynamic of that you will have if you study theoretical the system. And what they did is they prepared essentially one-dimensional systems in a super lattice and prepared some initial state that was essentially like empty and occupied sites. And then they let this evolve with a Bose-Howard-Hamilton. Okay? So what is shown here is the density in the odd sides start at 0. And what you see is that essentially when you release that, make the unitary evolution, essentially the density changes and somehow like flattens to a value 0.5. Now there are some things that are important in this plot. One is the theory are this line, and you see that in all the plot the theory stops at some point. And this is because this is an unbiased theoretical computational approach, and this is just telling you that simulating quantum dynamics is very hard with classical computers. And essentially, this is a hard wall for the computation. So it's very difficult to go beyond that. And that's why these experiments are so important. So the other thing is that how close the theory is to the experiment. So there are two sets of theoretical data. The continuous line is if you only put nearest neighbor hopping. And, but if you do the band structure calculation, there are some next nearest neighbor, and this is the dashed line. And you see how close that is to the experiment. So essentially, it's telling you that the actual evolution in the experiment is pretty close to the unitary evolution that we can simulate theoretically with this Howard model. And the other thing that one can do, because there are a lot of discussions in this topic of thermalization about local versus non-local observables, is this is the local density, and one can also look at the momentum distribution function, which is the Fourier transform of the one particle density matrix, and this is the experimental results, and this is the thing. Okay, so essentially they are very good simulators of the unitary dynamics. Now let's see how we can think of all this in here and how we can relate it to the question of thermalization. So what is it that one is doing in, for example, in the numerical simulation? So one is doing the unitary evolution of a system. So what is done there is essentially you prepare the system in some initial state that is not an eigenstate of your final Hamiltonian that is driving the dynamics. The system is isolated, so the energy is essentially conserved. And we are interested in some observable, the density, the momentum distribution function, which it's evolved following this expression here. And you see this is the time evolving wave function, which is just the unitary operator acting on the initial state. Okay? So you see this wave function, all it's doing is just kind of rotating there. But now what is it that we are going to call thermalization? It's not going to be a statement about the wave function. It's going to be a statement about what's happening with the observables. And what we are going to say is that the system is thermalized if after some time it has relaxed to something that is almost time independent, and then if you do the time average of the observable, you can describe it with one ensemble of statistical mechanics. Let's say microcanonical, canonical, or grand canonical. Okay? Now, what is the problem if you have unitary evolution? Well, the problem here is that you can write the initial state in terms of the eigenstate of the Hamiltonian, plug this in here, and you get an exact expression for the evolution of whatever observable you have. Of course, this sum here runs over an exponentially large number of states, so this is very difficult to calculate, but you see it's written in terms of the matrix elements of your observable. Now here you can just take the infinite time average of this expression, and in general we expect that generic systems, they will not have the generacies. So when you do that, the off-diagonal terms go away, and essentially this is the result that you will have out of the quantum mechanics. Okay? So, and this is something that we call a diagonal ensemble, because you can write this as a diagonal density metric. It's like the time average of the density metric of the time evolving system. So now you see the problem. So the problem is that this exact result from quantum mechanics depend on the initial state from the projection of essentially initial state in all the eigenstate of the Hamiltonian, right? So there is a lot of information here, while here it only depends on the energy. So, and then one question is, how can these two things be equal? As a matter of fact, you could even make it stronger. You could say whether it even makes sense to ask that question, because we know that in these ensembles, the states that weight, right, that are taken into account are those that are very close to the energy of the mean energy, right? So on the width, it goes to 0 in the thermodynamic limit. Well, if you look at this here, these C alphas, in principle, you could say they could be anywhere in the spectrum, okay? So these things, they don't have to be even like closely related. Right? Now, that question we can answer analytically, at least for the kind of non-equilibrium dynamics that we've been studying, which are the quantum quenches. So essentially, these quantum quenches, that similar to what is done in the experiment, what one does is to take some initial state that is an eigenstate or just a thermal state of some initial Hamiltonian, and then you change the Hamiltonian. Now, the important thing in this proof is that the change has to be a sum of local operators, okay? So if you have some long-range interaction, then things may be very different from what I'm going to be saying here. But if they are the sum of some local operators, you can compute this energy density, the width. This is essentially the definition. You can show that it's equal to this. And now, essentially, because of this summing here, is this expression that you have. Like, there are no long-range correlations. What you can see is that this term in here, well, it will vanish when the distance between J1 and J2 is beyond some number. And what you are going to get is that this energy width scales with the linear dimension of the system. This sigma is the dimension of the part on which you are applying the quench, divided by 2, right? And now you see the full spectrum diverges like L to the dimension of the system. And if you compute the relative width, you see that you get this expression, which is something that vanishes in the thermodynamic limit. Okay? So essentially, as long as your interactions are local, we are doing fine. So it makes sense to compare these two things. Okay? They still don't need to be the same, but at least it is a valid question. Okay? So now let's take a look at essentially what happens if you do the actual dynamics. So we decided to look at this, do some numerical experiment. And for that, we took Harcourt bosons in 2 dimensions. So this is not an integrable system. So, and we put it in some configuration like this. The idea was to have some kind of Gedanken experiment, like the one we think in our statistical mechanics class, like to have some container inside some bigger room, and then just open it. And essentially, we considered 5 bosons, 21 lattice sites, and we did the full non-equilibrium dynamics. Okay, there are no approximations. We are really computing the full spectrum and doing the entire non-equilibrium dynamics. So, and now we can go back to these expressions that I showed you before. And there is a point in which you could have told me, like, you are not allowed to do this. And this is the point that you could have said that. So you see, I showed you this is the exact expression, and I told you, okay, let's take the infinite time average, and we get this. But you could have told me, look, but if your system is very big, right, the energy spacing is going to become very, very small. So essentially, for these phases to go away, you will have to wait infinite times. So essentially, this could be completely irrelevant to the actual dynamics in your system. Okay? So, of course, that will depend on what these matrix elements are, which we are going to see by the end of this talk. But we decided to, okay, let's take a look at the actual time evolution versus this result here. Okay, so this is essentially the momentum distribution function of the initial state, and this is this infinite time average that we can compute theoretically because we have essentially all the information about the spectrum of the system. Now the question is how do they relate when time starts passing there? So this is how it looks like. So there are only 5 particles, and you see that very quickly, essentially, the system relaxes to this kind of infinite time average. And even with 5 particles, the fluctuations are very small around that value. Okay? So essentially, the time that it takes for the system to relax to this distribution is the time that it takes to a particle to go from one corner of the lattice to the other corner and back. Okay? And then one sees this.
The lattice had hard boundary conditions?
It's open boundary conditions.
Open, not periodic.
So these are open boundary conditions. So this is how it looks like actually. This is the zero momentum occupation. This is what you saw in here, and then you see it stays there for a very long time. Now you could compare, and now the next question is how is that infinite time average related to the expectations that we have from statistical mechanics? So you can do, for example, a comparison between the observable and the prediction of the canonical ensemble. And you have to fix the temperature, and you can fix it so that that ensemble, the mean energy, is the energy of the time evolving state, which gives this temperature in this case. And you see it's close, but there are some differences there. Now, of course, this is a very small system, it's isolated, so it's better to do a microcanonical calculation, which we did. And what you see is that there is essentially an almost perfect agreement between the infinite time average and the microcanonical prediction. So despite the fact that we had this expression that looked like totally unrelated, they do look thermalized after some time. Okay, and that's what we are going to be discussing in a minute. Now, does that happen always? Will all quantum systems do that? Next thing that we can do is essentially the same system, but now put it along one-dimensional chain. Okay, so we can put the particles initially here and open this link and allow it to expand. Now, this model in one dimension is integrable. And if you do the dynamics, essentially you get something like this for the infinite time average. Microcanonical and canonical give you something like this. Now, this system is small. If you study the thermodynamic limit of that we are not going to be discussing here, so we work on that here, you find that the microcanonical and the canonical become the same, but the time average is different. Okay? So essentially, doesn't thermalize. Now, for the rest of the talk, what we are going to be discussing is what happens between this regime of integrability and non-integrability, and see how that relates to the experiment. So I think at this point I can take questions that you may have, because this is kind of setting up, what the problems are, what the questions are, and then the rest is going to be essentially discussing the inner workings of the quantum dynamics. So any question about?
And into this, you've also thrown the trap, the harmonic trap.
In this case, I didn't throw. This is just an open. It's like a box. In this case, it's a box. Yeah.
So there are no experiments for this one.
For this one, well, I mean, boxes probably one could do it. I mean, there are other cases that we studied with the trap, but yeah, no, in this particular case, there is no trap. So another question over there.
You don't need to make it 2D to make it non-integrable.
And in that other case, no, I don't need it. You mean you can put some extra interaction next nearest neighbor?
Yeah, or even for the second neighbor hopping.
Exactly. So that's what we're going to be doing in the next slide. So this one was just by geometry. Okay, so I made one integral, one non-integral just by geometry. But indeed, what we're going to be doing next is just use a parameter that will allow you to tune between the two. So any other question there?
In the non-integrable case, have you put any finite size scaling of how these?
I'm going to show you a finite size scaling, but in the 1D case. I mean, 2D is very hard because it's an exponential problem, so we cannot control it. But in 1D, I'm going to show you the scale. So, other questions?
Have you looked at higher order correlation functions?
We are going to be looking at next. So, at this density, and one particle, yeah, right. We are going to be looking at that in the next slide. So, other questions? Okay, so then we are ready to go into this, into the the details of how all this works. So, and the way we're going to do it is essentially following that very idea that was mentioned there, is we are going to take a model now in one dimension that one can tune between integrability and non-integrability without changing the geometry, just by changing Hamiltonian parameters. And this essentially, again, hardcore bosons with nearest neighbor hopping, next nearest neighbor interaction. So this part is integrable. And then this T prime and B prime, so next nearest neighbor hopping and next nearest neighbor interaction, that breaks integrability. Okay? Now, since we want to do scalings and so on, what we're going to be studying is a case with periodic boundary conditions, because then we can use symmetries to make the calculation more efficient. And you see, we can now study the 8 bosons in 24 lattice sites. So the Hilbert space is over 700,000 states. And then if you look at, you split it in different sectors, so the largest matrices we have to deal with is these 30,000 states. Okay? So, and then what are the quenches? So you see, the other quenches were kind of geometric quenches, right? Like you had some initial state, it was part of the lattice, and then you allow it to expand in some other part. So in this case, the density is homogeneous. So what we change is this parameter, the initial hopping and the initial V, so they are quenched to some final value. So essentially what we do is prepare an initial state, an eigenstate of this Hamiltonian with some parameters, and then change those parameters at some time, and then look at the evolution. Okay? So that's what's done in that case. So what is shown here again, just to look at that for several observables, this is the momentum distribution, which is a Fourier transform of one particle correlations as a function of k, and this is the infinite time average and the initial state. So let's take a look at how that looks. So this is pretty much what happened in the other case. So you see that the system essentially, even in 1D, it relaxes to this infinite time average. Okay, so that's very similar to what we saw before. But now let's take a look at another observable.
Sorry, I feel like I've missed something crucial here. You're comparing this particular observable to tell you about whether or not it's thermalizing, but I mean, wouldn't, naively I would expect you'd like to ask the question, to what extent is this approximating a canonical ensemble of some nature?
Right.
And
so far here, wait, let me just clarify something here.
Yeah.
Here, we are not talking about thermalization. All we are probing here is the system relaxing to that infinite time average. That infinite time average may be completely different from the thermal. All this is quantum mechanics.
Right.
There is no statistical mechanics at this point. Okay?
So the concept that sort of there's going to be a natural tendency to a distribution over all the states of equal energy is not yet implied.
Not implied.
Okay.
So you need more than that.
No, it's fine. Thanks.
But now we can look at another observable, like, for example, this structure factor, which is a higher order correlation, is the Fourier transform of density-density correlation. And let's take a look at what's happening. So this is the initial state, and this is the infinite time average, and we can look at it. And this is what happens. So essentially, it's very similar to what happens in the other case. So it does relax to that infinite time average. So far, there is no statistical mechanics. Okay, so now let's be more quantitative, because I'm just showing you some dynamic. And so how do they actually scale? What is the behavior? So what we can do now is compare this time evolving occupations with the infinite time average, right? So if this relaxes to this has to go to 0, right? So, and now I'm showing you result for different values of this hopping. So this is far from the integrable point. This is the integrable point. Now this column is for the momentum distribution. This column here is for the structure factor. So, and you see, essentially all the results look very similar. So initially there is some kind of quick reduction of this delta, and then there are fluctuations. Okay, the fluctuations are larger, close to integrability, than away from it. But I mean, qualitatively, they are essentially similar.